Hello everybody, welcome back to another video. In this video we're going to explore logarithmic functions. In the last one we looked at exponential functions, and we're going to take a closer look at their relationship to one another. So let's just begin by trying to understand what logarithms really mean. So we have this definition here. I'm going to keep this above, but before we even read that, let's just see it with an example and then take a look back at that definition afterwards. So let's suppose that we want to simplify something like log base, let's say log base 3 of 27. Well, now let's glance at the definition. Log base a of x is the exponent to which a must be raised in order to give us x. Okay, a little bit of a mouthful, but let's now transpose each of our symbols. Let's transpose the 3 and the 27 into that definition and see what comes of it. Log base 3 of 27 is the exponent to which 3 must be raised in order to give us 27. So, in other words, we have to solve the equation 3 to the x equals 27, where x is this quantity right here. So log base 3 of 27 is the solution to this equation. 3 to the x equals 27. So the solution to this equation, notice that if we take 3 to the third power, we get 27. So x must be 3. Or in other words, log base 3 of 27 is 3. Let's do another example, maybe with some different numbers other than so many 3s. Let's look at, how about in blue, let's just do, let's take the log base 2 of 32. Okay, well that's the exponent to which 2 must be raised in order to give us 32. So 2 to what power, so this is equivalent to saying 2 to what power is equal to 32. And you know, if we multiply 2 by itself, let's experiment. If we do 2 times 2, that's 4, so 2 squared is 4. We multiply by 2 again, we get 8. By 2 again, we get 16. And by 2 again, we get 32. So that took us 5 multiplications. We got 2 to the 5th power is 32. So, in other words, log base 2 of 32 equals 5. Because 2 to the 5th power is 32. So the proper way to understand logarithmic functions is really just to put them in terms of exponential functions. That's the nice, easy way to make sense of them. So earlier I said that exponential functions and logarithmic functions are inverse to one another. So what I want to do is take the time to plot the inverse function of 2 to the x. Well, the inverse function of 2 to the x, so maybe I'll plot this, make this smaller. Let's say, I'll write it right here for the name y equals, or maybe I'll say y inverse, because it is the inverse. The inverse of 2 to the x would be log base 2 of x. And what it looks like, I'll just do it in, maybe I'll do it in a different color. Maybe I'll do it in, I'll just do it in red, make it simple. It looks something like this. So it's not the perfect picture, it doesn't quite level off quite like that, but anyway, it looks something like this shape, right? So the horizontal asymptote that we had with y equals 2 to the x kind of became this vertical asymptote. But the neat relationship with inverse functions is that they're symmetric to each other about a specific line. So in particular, if we draw on this line y equals x, maybe I'll do it in blue or purple. Let's do purple. In purple, we draw on the line y equals x. Provided that I actually drew this inverse function incorrectly, it should be the case that if I were to reflect this graph of y equals 2 to the x, this curve right here, if I reflect it about this line, imagine I take this and I pick it up and I throw it over this line like it's a fence or something, and I'm taking this all as one piece and throwing it over the fence. It's kind of a weird way to think about it, but that's how I picture it. You get this red curve, which is the inverse function. So that's the geometric relationship between logarithmic and exponential functions. They're reflections of each other across this line y equals x, which effectively is equivalent to that to swapping the x and the y coordinate, swapping the x and y coordinate around, which is what we do with inverses. So anyway, not to go into too much detail there, maybe we can end the video by solving a logarithmic equation. So let's pan off to the right side. Let's solve one or two of these. Let's say that we want to solve, yeah, this is great. So we'll have two nice examples. Say example 1. Let's just suppose that we want to solve, let's go with log base 2 of x is equal to -3. Okay, remember what this means. This is equivalent to saying 2 to what? Or 2 to the number that's over here, 2 to the -3rd equals x. Oh, this is nice. We immediately get the solution. It's just 2 to the -3rd. But what is 2 to the -3rd? That's 1 over 2 to the 3rd, which is just 1 over 8. So we just solved that logarithmic equation. The answer is just 1/8. Awesome. So log base 2 of 1/8 is -3. Perfect. Let's look at one more example. So now let's take a look at one that's a little bit different. Let's say that we've now got the log base x. So now our base is the variable. Log base x of 16 is equal to 2. Well, let's just remember what this means. What it means is we take the base x, we raise it to the second power, set it equal to the inside, 16. And now we solve the resulting equation. Well, we know that this, by section 8.1 in the principle of square roots and stuff like that, we know that x would be equal to plus or minus 4 out of this. And then we have to think of whether this makes sense in the context of the problem. Well, it turns out that we don't want negative bases, right? Remember that from last video. We make sure that our bases are positive and also that they're not equal to 1. So we kind of throw out this -4 solution and we just retain x equals 4. That's the only one we'll actually hold on to. So in other words, x equals 4 is the solution to the logarithmic equation in example 2. And so yeah, I think that's all I would like to talk about today. We're running out of time, but in the next video we're going to take a look at some properties of logarithms. So I hope you all have a great day, and we'll see you in the next video.